Okay, today's the 26th. Let's see who's there. Time is almost 9. (26:02). Hey, there's a couple already. Good morning, Tom and Larissa. 4 points there. And we also got Riley and Lee and Magdalena. 4 points to all of you, and good morning. Super. And now we've also got Tadashi, hello, and Natalie, hello. So glad to have you all here. Sarah is here as well. Good morning, Sarah. Thanks to all of you coming and being so prompt. Bria, good morning to you. And I got a bunch more. I got Julian L., Isabella, and Lily. Things are going well. Thank you, Lily. So let me write y'all down. Julian L. is here. Lily is here. And Isabella is here. Shilpa is here. This is great. Isabella's here. Shilpa is here. And Merla and Nicholas are both here. Dynamite. Super. And Noah's here as well. Very good. Still looking for, and Deacon's here. Great. Still looking for Julian K., Aiden, Lena, Christian, Dominic, Ali, and Vincent. If any of you are here, say hello. But that's a mighty good start. Thank you, all of you, for being here, being on time. Can we next week not have a live stream on Wednesday, but on Monday, the 4th, or Friday, the 8th period, due to the Schnupperwoche? I don't understand the Schnupperwoche, Magdalena, because you can't be there. Are they going to invite you to live streams? Is that what we're supposed to do? I honestly don't know. Julian K., thank you. Good morning. Thanks for being here, Julian. Yes, okay. Oh God, I don't know, Magdalena. I guess I gotta see what my schedule is too. We go visit AP and Lifestone's courses to see how they're like. I tell you what, let's do it this way. I don't know what Lifestone's courses you are all going to go to, or AP courses, okay? And I don't know if I can plan. Hello, thank you, Dominic. Dominic is here. They're Google Meets. Okay, that's fine. But the problem I have is I don't know when you guys are going to be gone, when you're not going to be gone. Did they send you a list of times to sign up, or you just sign up anytime there's any AP or Lifestone's course? In other words, is there any way I can know when you guys will not be here? Because if you're going to be here gone at different times all week, then I'm not going to change my schedule. But if you're all going to be gone the same hour, then I will change my schedule. Okay, let's see what you're saying. They said that yours excused if you go to the Google Meets while you're supposed to be in class. Yeah, which is fine. And so the normal class you can probably watch on YouTube if you go to a AP or Leicester's course instead. Let's just do it that way. I think that's the easiest way because I have no idea when you're all going to be gone, Magdalena. We definitely have time Monday the 4th and Friday the 8th. Okay. Monday the 4th sounds fine. Friday the 8th, I don't know. I don't know because I don't know what my schedule is. It's different. Yeah. Okay. I'm guessing it's different for each of you. Okay. Last call for people before I set this aside. Do I have an Aiden, a Lena, a Christian, an Ali, or a Vincent? Okay, well, we will have a live stream Monday, so I'm glad that's not going to interfere. So you'll all be there Monday. I'll have to see about later in the week. I don't know what I'm going to do. Okay, because often I have meetings and live streams as well with other projects also, and my ED committee. So I'll have to see. Thank you for the heads up, though, everyone. I'll try and remember that. If we can do Friday 8th, we will. If not, we won't. So we'll see. Okay. Also, I'll make an announcement too. You probably received it now, but if you have questions about AP chemistry, that's what I teach. Let me know. Some of you have asked me questions already. That is most welcome. And there's a video I made to tell you a bit about the course as well. So watch the video, ask me questions. All will be well. I have lots of smart 10E students that would be most welcome in the course. Lena, thank you for joining us. That is good. Okay, so I got a lot on my agenda for you today. And one thing I want to do we got to finish up one last drawing together based on the experimental work we did last week. And then there's a question I got from somebody I want to take and answer that too. Maybe I should answer that first. Yeah, here it is again. Okay. Why some waters are attracted to other waters, but sometimes attracted to other elements. Okay, let's talk about that. Let's answer that, show up on everybody with a question. You ready? By the way, my 8th graders suddenly thought that because it's online, they don't have to take notes anymore. This was kind of wishful thinking, but you guys know anything I put on the whiteboard, you should put in your notes, right? Okay, I think you know that. Some of my 8th graders, oh no, we don't have to take notes anymore. How wonderful. Okay, well, that would be not true. Okay, so write it down. If you can't get it all, then watch the YouTube again and then write it down. Okay? All right, so the question we could ask is, when do waters only attract to each other and when do waters attract to another molecule? Question mark. So when do waters attract? When do waters only attract? Bad English. When do waters only attract to each other, and when do waters attract to another molecule? Question mark. Okay. The simplest thing to remember is like dissolves like. So if I got a dipole, it dissolves in a dipole. And by dissolves, I mean, okay, is attracted to. So in other words, if they've both got a dipole, like water does, then they're going to attract. And I'm talking about a permanent dipole, permanent, not these temporary ones in London dispersion forces, okay? Okay. And ion dipole force also allows something to be attracted to water. I'll say if ions dissolve, they, let's write that a little more chemically. That's really sloppy, sorry. If ionic solids, let's use the right term. So, and if ionic solids dissolve, then, no, not then, the ions will also attract to the waters. So, to be really blunt about it, you got two cases where water attracts to somebody else. Dipole, in other words, for water, usually hydrogen bonding, okay? Or ions that dissolve in the water, like NaCl, Na plus and Cl minus, okay? Usually things just with a 1 plus charge or 1 minus charge. When do they not attract? If a non-dipole is dropped in water, to be really blunt, there's no, let's see. Let's just write it this way. Then the waters stay together. Let's see if that makes sense. So if a non-dipole is dropped in water, then the waters stay together. Yeah, that's what I want to say. Shilpa, does that help a little bit? And others too. I think it'll be even more clear when we do another example from our lab work last week. I know that's a lot of writing. Let's do a picture to finish off our work from last week. By the way, wait, before I start, let me ask, okay, thank you, good. Are there any other questions about the assignment? I think it was due already anyway. I can't remember if it's due yesterday or today. Drawing the drawings. Are there any last questions about drawing those drawings? Because that's a skill I want you to be able to do. We're going to do one more today in a second. Due today at 4. Thank you, Lee. Are they going okay, or did you have questions? Were you able to draw them effectively? Because if you got a question, now's a good time to ask. I'm going to erase this while you think. All right. See if anything comes up. Okay, thank you, Natalie. Therefore, let's go on and talk about one last thing from last week. Okay, so remind me, folks, did we add octanol to water or heptanol with the OL at the end? Octanol or heptanol? Can somebody look back and see? I forgot which we did this year, and I'd like to draw the correct picture with you. So I recall, all did not dissolve in water. Heptanol. Thank you, Priya. Thank you, Sarah. Okay, so heptanol. It actually doesn't matter, but I like to do the same one that you had. Why not? Okay, let's take a look at a heptanol. Hepta is how many, folks? Thank you, Tom. Hepta is how many? Heptanol. And the OL means I got what on the end? Two questions. 7. 7 is good. And if it's OL, what's on the end? 1, 2, 3, 4, 5, 6, 7. N, O, and an H. Thank you very much. Good. Lots of folks had that. Larissa, Shilpa, Priya, and Sarah all had that. Nice. So there's OH at the end. I don't have to do that. I'll just write OH. Okay. All right, I'm going to draw another one down below. And let's put the OH over here. It doesn't really matter. Now, you might say, oh, it's got an alcohol. I remember if it's got an OH on it, a hydroxyl group, that will attract water. Well, yeah, kind of. Let's put a water over here. Okay, so we will get a water that will attract this. All right, so there's one. And there'll be some attraction here. A little bit of hydrogen bonding, but not much. Why? Check this out. I'm going to put a bunch of waters in the middle here. Watch this. And okay, so there's a bunch of waters. I put like 3 waters in the middle. And you know what? And it could fit more, okay? This is just like a drawing, all right? So let's circle these. Why am I doing this, okay? Here's the point. Whoa. Most waters are not near the OH of octanol. No, sorry, heptanol. So, no hydrogen bonding, or very little. I'll say little. What that means is, gang, the waters are going to stay together. They're not going to play with the octanols because most of the octanol, look at all those C's. Look at all those C's. Most of the octanol molecule is just a bunch of carbons with hydrogens. Most of heptanol is a non-dipole. Now you might say, but Mr. Weiss, but it dissolved in ethanol. Well, let's check out ethanol instead. Look at this. OH. Okay, now notice how ethanol is a lot smaller, right? Isn't the OH more important here? Because the chain of C's is way smaller. So with ethanol, if it's a small molecule with an OH, the OH really matters. However, if it's a big molecule with an OH, the OH doesn't really matter much. The waters are going to stay together. They're not going to play attraction with the long chain of C's because this would be like a non-dipole. Okay? In this little one, the non-dipole is pretty small, so the dipole part is, relatively speaking, takes up a bigger portion of the molecule, the OH. So the OH in ethanol is important. So like we drew last time, let's do it in red. The little waters are very attracted to ethanol because most of the molecule, well, a good percentage of the molecule then has spots that can hydrogen bond. That OH can hydrogen bond with the waters. So my point is that size matters. Here's what I mean. If the non-dipole side is big, then the molecule is mainly a non-dipole. If the non-dipole size is small, then it's mainly a dipole molecule. So ethanol is mainly looked at as a dipole. Heptanol is not. Okay, I don't know how many of you did this. If you ran off the sheet I sent you, printed it of alcohols, pull that out now. Okay? I want you to look at all the alcohols. It goes from what? Probably methanol down to, I don't know, heptanol, octanol. Okay? That's the question, Tadashi. We're going to answer that now. If you have that sheet, if you don't, you're going to have to like either pull it up on the computer or look it up later. So I sent you this data sheet, and it has a couple of tables. One is the melting and boiling points. Now, if it's got a dipole, well, okay, let's come back to that. Okay, never mind. Solubility in water. Let's just talk about that. That's the main thing. Notice that the top two, methanol and ethanol, are soluble. Propanol a little bit, but after you get, Tadashi, to about butanol, and then the bigger ones after butanol, pentanol, hexanol, heptanol, Tadashi, those suckers are all too big. They got too much of their molecule that's non-dipole, and they just are not very soluble in water. I think there's numbers that show you the amount that they're soluble. So probably a big number for ethanol, maybe, and for methanol, ethanol, but then propanol smaller, and then probably you get to about butanol, Tadashi, and probably from butanol to larger, the non-dipole part, like up here in heptanol, just is way too big. Now you might say, this sounds confusing. I'm going to give you a way to like think of it, why it's this way. Okay? All right. Anything other than what we're continuing with? Any questions on this? Because I need a little whiteboard. I got to erase this. And the simple answer, Tadashi, is look at the data. The data will tell you. You don't have to memorize anything. Tadashi, you'll always have data to answer that. Okay? Unless you have two that are really different, like ethanol and octanol or something, then clearly the OH matters with the ethanol, but not with the octanol. Okay, so there's a couple words we need for all of this year. And they're pretty cool words because they're going to make total sense to you. Let's take heptanol again. So example, again, heptanol. All right, draw that puppy out one more time. 2, 3, 4, 5, 6, 7, OH. Kaboom, boom, kaboom, boom, kaboom, boom, 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 boom. Okay, we're done. Remember when I told you this part was more like a non-dipole? That's one way to say it, but there's another word for this part. And it's kind of a cool word. You ready? The word is called hydrophobic. What does hydro mean? Anybody got that phrase from Latin or Greek? Hydrophobic. What does hydro mean? Water. Thank you, Tom. Super. Several others had it too. Lily, Merla, and a bunch of you. Okay, great. Woo, thanks, everybody. Well done. So, and if a phobia means you're scared of something. So hydrophobic is a portion of a molecule, quite frankly, not attracted to water. Not attracted to water. Why? Because it's a non-dipole. Due to non-dipole. Now, phobia sounds like it's scared, but it's a nice way to remember it. But molecules don't have little feelings, okay? So we can't say that this part is scared, okay? Because that would be really silly. Instead, it just is not attracted to water. Okay, then, can you guess the other word? Is this a representative of LDF? Yine, it refers, Lily, to it refers to intermolecular forces, but between water and whatever. So not an LDF, but a IMF, intermolecular force. So what we're saying here is there's not a big force between this molecule portion and water. There's not a big attraction there. Yeah, some of you have had this. I love it. God, did you guys know that from another course? Or did we talk about this already? How do you know that? Look at that. I had a bunch of you. I had Tom, Magdalena, Natalie, Shilpa, Sarah, all knew that. So this portion is called the hydro. What did you just Google it? Whoops. Be nice if I spelled it right. Hydrophilic. Hydrophilic. From Bio. Oh, see, you guys are so good. Was that Mr. Lee? I got to pat him on the back, at least virtually. Okay? So hydrophilic means attracted to water. So now, back to Tadashi's good question. How do I know whether it's going to dissolve in water or not? It's like a trend, Tadashi. So we say, okay, the greater the size of the hydrophobic part, the less soluble the molecule is in water. Let's just shorten that. How about we say less soluble in water? So that's a cool little star thing. I think that'd be really helpful if I was a student. So, okay, the greater the size of the hydrophobic part, right? The part that's a non-dipole, the less soluble that sucker is in water. Makes sense, right? And from Ms. Galloway. Ah, thanks, Sarah and Shilpa. Good. Dynamite. She's tops. Good old Ms. Galloway. All right. I think that helps you guys think about things. I hope so. I hope so. Okay, now, question for you. Those that have the alcohol sheet, can you answer me this question? As the molecules get bigger, going from like ethanol to whatever, heptanol, octanol, what happens to the melting and boiling points? And I'll answer your question in a sec here, Shilpa. What happens to the melting and boiling points as the alcohol gets bigger? Is there a trend on your table? And Larissa and Natalie say it gets higher, and so does Isabella. Ollie, you're mighty late. Okay, I can't really give you points, Ollie, so send me a copy of your notes, Ollie. Then you can do that. You're going to need to watch the video. But at least you get this part of it, okay? Send me a copy of your notes on the other part later. Okay, right. So, what was I doing here? Let's use the alkan. Oh, that's a German. Sorry. I use English and German. Alcohol. German. Alkanol. Molecules as they increase in size have higher melting points and boiling points. Why? Okay. Let's compare like butanol and hexanol. Okay, 1, 2, 3, 4. Boop, 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 boop. And 1, 2, 3, 4. Boop, 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 boop. And hexanol. 1, 2, 3, 4, 5, 6. Shaboom, boom. I better put my C's in here, my H's in here. Don't want to get sloppy. And another one below. 1, 2, 3, 4, 5, 6. Hexanol. Shaboom, 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 shaboom. Okay, whoa. All right, so why did I do all this with you? Okay. For both of these, back to what I talked with Tadashi about a moment ago, for both of these, the OH is pretty unimportant. I'm sorry, the rest of the molecule is just way bigger. The hydrophobic part is much bigger than the hydrophilic part. The hydrophilic part is just a little hydroxide at the end. So what that means is we're mainly talking about non-dipole molecules. So check out this. I got some non-dipole here, and here, and here, and here. And if it's non-dipoles and non-dipoles, my people, what will attract one non-dipole to the other? What sort of force attracts a non-dipole to a non-dipole? Hint, certainly is not hydrogen bonding. What attracts a non-dipole to a non-dipole? Yes, that's the abbreviation. London dispersion forces, right? Or van der Waals Kräfte in German. So we got it. Boop, 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 boop. And here we got it. Boop, 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 boop. Now, so why does hexanol has a higher, let's say, melting point for starters, due to What, gang? What's different about these two? It's a lot bigger here. So there's, thank you. Yes, London dispersion forces. Thank you, Magdalena, Lily, Tom. Thank you for knowing that. So why is the hexanol boiling point higher? What did I have to draw more of here? What's going on? Yeah, I've got more London dispersion forces. Let's call it a greater, see what others folks say. Hydrophobic molecules are larger. Yeah, okay, good. Stronger force. Thank you, Shilpa. That's probably the best way to say it. So we've got a stronger due to stronger, I'll abbreviate London dispersion forces as Lily and others did because my board's so small. Higher melting point due to stronger London dispersion forces. On a quiz or test, please write it out once, and then you can use the abbreviation on the rest of the test. You know what I'm saying? That's what you have to do in AP Chem too. So, but for now, we'll say we're going to leave it that way so I can save a little space. Higher melting point due to stronger LDF in larger hexanol. Right? It's bigger, it's got more surface area, it's got more electrons. Remember, all that matters. And look at this, I've come so far that I think it was Shilpa's question is now gone. Shilpa, you'll have to ask it again. My apologies. And I see other questions too. Yes, good. Natalie, right. Hexanol has more surface area and more electrons. So there's more temporary dipoles that can, well, so there's larger temporary dipoles that can occur with this. And so that will keep these guys more together than these guys. All right? The OH at the ends, it just doesn't matter much, folks. It's just too small. The hydrophilic part is too small to matter. Yeah? Does that make sense? I hope so. I think you're doing pretty well with this, folks. Good. All right. Let me look and see what else I want to talk about today. Okay, we're going to go into a little chemistry. I'm going to introduce it for next week unless you got some questions. Okay, thank you, Shilpa. What I'm going to send you next week is something about comparing forces. I'm going to send you a little assignment on Monday. So let's call it comparing forces assignment. And that'll be given next Monday. All right. The phrase you'll need is bond. The phrase is bond energy. It's the energy required to break a bond. And I'm going to call it intermolecular forces energy. Woo, that's a long phrase, huh? And that would be the energy to break intermolecular forces. Can I abbreviate that here to IMF? Intermolecular molecular forces. That's in the business quite often used as IMF. Okay. Example. Oh, got a question here. um, To be honest, Magdalena, London dispersion forces are always there between molecules, long as I got separate molecules. But sometimes the more important force is either dipole-dipole or Magdalena. If it's got a H and a FON, the F or N, then hydrogen bonding is more important and stronger. Okay? So you're going to see that these vary. I'm going to give you a sheet of numbers with some bond energies comparing pardon me, comparing ionic, covalent, and metallic bond strengths and intermolecular forces energies. These will be numbers comparing London dispersion forces, hydrogen bonding, also like dipole ion forces. But here's the deal. It's a range. None of these has an exact value. So I'm going to put a little. These all have ranges. You know what I mean by range? Like 5 to 30 or 100 to 200. That would be a range. These all have ranges due to different atoms and molecules. In other words, the world is complex. But not infinitely so. When you get that data, you're going to be able to answer questions. And I'm going to ask you them now, and you can answer them when you get the data. What do you think? Which numbers do you think will be stronger? The bond energies or intermolecular forces? Well, you'll be able to answer that on Monday when you get the data. And which of the intermolecular forces do you think will be the most strong? Which will have the highest numbers of energy to break them? Which do you think will be the strongest? Hydrogen bonding or London dispersion forces, dipole-dipole, ion dipole? Well, you'll find out on Monday, but I bet you have some guesses already. But if they vary a little bit, so I don't want you to say, oh, it's got London dispersion forces. That's always weak. Sometimes it's not so weak if they're bigger, like octanols or something. All right. Okay. All right. I'll stop fiddling and let's see if you have any questions. Good. The other thing we'll talk about next week is fermentation. In other words, making alcohol, mainly making ethanol, which is by far the most common alcohol in our society. And it's used for cleaning, it's used for liquor, it's used for all sorts of stuff. Okay. So we'll talk about how it's made and what chemistry is going on to make that. You might have had that in biology too, I'm guessing, from somebody like Ms. Galloway. Hope so. If you have, then this will be easy next week. Okay. Any questions from you on all of this? It's fairly complex. That's why we're taking time to talk about it. We'll continue next week with, this assignment to help you understand it better too. Okay? Good. All right. I'm not going to start fermentation with 1 minute left. So I'm just going to let you go on an early Friday. And thanks everybody for being here. Let me know if there's something you need to ask me about AP chemistry. You may do so in email. Okay? Thanks everybody for being here. Good participation as usual. Bye-bye.